So hello, everyone. My name is Christina, and I work at 84 Codes as a full stack developer. I'm also a project lead for our open source message broker, LavinMQ. So I'm based in Stockholm, Sweden. And with me today, via Zoom, I have my colleague, Nyior. Do you want to introduce yourself?
Yeah, sure. Hi, everybody. Nice to meet you all, even though I can't see anybody. I am Nyior Clement, a developer advocate at LavinMQ by 84 Codes. So before 84 Codes, I'd worked as a Python engineer where I'd used Django a lot, and then at some point, fastapi too. I currently live in Abuja, Nigeria. Yeah, that's it. Over to you, Christina.
Awesome. OK. So like we said, we come from 84 Codes, and we're standing in a booth in the big hall among all the sponsors. So maybe I've met some of you, and the rest of you I'm eager to meet. So please go by the booth, and we can talk some more. So 84 Codes was founded in 2012, and we specialize in automating and hosting open source cloud services. Mainly, we specialize in messaging services, but we also host database services, like PostgreSQL. OK, forgot to. Here we got it. OK, so our flagship product is CloudAMQP, which hosts RabbitMQ and LavinMQ as a service. So which basically means that we set up and configure RabbitMQ and LavinMQ for our customers. And so today we're here to talk about efficient communication solutions for your Python microservices with our in-house developed message broker, LavinMQ. So now some of you might be familiar with microservice architecture already, but I thought that I would give it a minute or so to just lay a foundation for us to build upon. So first I'm going to talk about what are microservices and what is message queuing. And then I'll do a short explanation on what LavinMQ is. And then I'm going to give the mic to Nyior, and he's going to walk us through a use case with Python. OK, so I think the best way to contrast microservices is to compare it with a monolithic architecture. So the monolith on the left here is tightly coupled, as you see. The services are dependent on each other, basically, to run. And in the beginning of a project, this is totally fine, because you don't have that many services or dependencies, really, to mess things up. But as your project starts to grow and the dependencies become more and more, it's more difficult to introduce changes or even scale individual services. And a bug in one part of the application can really affect the whole system and even cause the application to go down. So you can understand why engineers start to look for other, more maintainable solutions for the long run. And that's where microservices come into the picture. These services are completely modular and independent from each other. Changes in one service won't affect the other services at all. And therefore, you have bug isolation. So the project problem that we had with bugs won't really be an issue here. And you also have more freedom in introducing new technologies or new languages. So you could, for example, have 3 services in Python, and you can have some services in Ruby, depending on what kind of expertise you have in your team, which is really neat. OK, so now with these services completely decoupled, how do they really communicate? So today I'm going to keep it simple. I'm going to talk about synchronous and asynchronous communication. There probably exists some type of hybrid solutions, but I think today it's going to be enough to just talk about synchronous and asynchronous communication. So beginning with synchronous communication, data moves from one endpoint of a service to another in what we call a blocking interaction. So a typical example here would be an HTTP request. So you send a GET request, and then you wait for a response before continuing with any other task that that service might need to do. So this doesn't really allow microservices to be fully autonomous. And the overall performance kind of gets impacted when you have to wait for a long line of responses, right? So this is not the most efficient way to communicate. On the other hand, we then have asynchronous communication. So this is outsourcing the message handling to a third party, which in our case now, we are using a message broker. So here you send requests or messages to the message broker instead of directly to the other services. The message broker will then facilitate these messages until they're consumed by the receiving service. So this service doesn't have to stop and wait for a response, which makes it much more efficient. Services send messages anonymously without needing any information on the other services, and so it only relies on the queue for the message to reach its destination. And this scales much better. The queue can hold like a large amount of messages, and the clients will just fetch them whenever they're ready or when they have the capacity. It's also more reliable. Synchronous messages often have a timeout where the messages will be dropped and you will lose your message. Here, the message queue will facilitate the message until the client's ready. Right, so now I'm just going to show you an example to really illustrate and make it really clear. So here we have two services. And when there is a high load on a service, there is a lot of traffic. Here, there's only 3 messages in the illustration, but we'll just pretend that that's a lot of traffic. And then the message queue is facilitating these requests. And this service that we have here in the beginning can continue on with whatever it needs to do while these messages have been sent out into the world. So now we can just wait here for a while until the client is ready to consume the message. So that's pretty good. Now, we have developed our very own message broker, LavinMQ. And it exists on GitHub as an open source project. And the LavinMQ project is all about using the experience that we have with hosting RabbitMQ for about like a decade now, and engaging that experience so that we can build on and improve of the parts of RabbitMQ that we think can be streamlined. So how does it work, really? Here you see an example of a data flow in LavinMQ. It's pretty similar to the example that I just illustrated, but with a few more details. So the producer, we have a producer service and a consumer service. The producer publishes a message with something that we call a routing key to the exchange. And the exchange component receives the message and routes it according to this routing key. So when routing, the exchange looks at this routing key, and it routes the message to the proper queue that the routing key is telling it to route it to. Messages will then stay in this queue until the consumer handles them, and the consumer handles the message in its own time. So that's basically how the message queue works. So now if you're familiar with CloudMQP or with RabbitMQ, this might seem really, really familiar. So what makes our solution different from RabbitMQ? So here we have the 3 main pillars of LavinMQ. So first of all, it's a super fast broker. It's optimized for performance, and we can benchmark throughput up to 700,000 messages a second, thanks to the priorities that we're making when we're developing. And hand in hand with this performance, we put a really high focus on resource efficiency. So we always try to keep the RAM footprint low for our vision of a more scalable broker, basically. And last but not least, we aim to make it feel like a really lightweight and simple broker. LavinMQ is simple to configure, and it's simple to get running. And we work really hard on our documentation, and we try to put up tutorials for you guys, so it's easy for you to just click around, get it set up and running. Easy. OK. So now, since we're on a time schedule, I can't go too much into detail about this broker, which I would really like to do. But you can come by the booth, and we can discuss things. And you can ask questions after the talk, and I'm happy to answer them. So now I'll give the stage to Nyior, and he will get into a use case that he has prepared for you guys.
All right. Thank you, Christina. Just to be sure, can you hear me? Christina, just help me confirm if you can hear me.
Yes, I can hear you. Can you guys hear? Everything is fine.
All right, yeah. All right, good. So let's try to build on what we've learned so far by looking at the use case with a sprinkle of Python. And to do that, I'd like to start in a very funny way. I'd want to tell you a story about my friend, Bob. The story of how Microservices on LavinMQ saved him. Now, Bob is a Python engineer. I'll tell you more about Bob very much later on, but for now, just know that Bob is a Python engineer at a certain company, So he's not so different from all of us seated here today since we work with Python. One day, Bob just had this crazy idea, Slack GPT. And Slack GPT is basically a Slack bot that brings ChatGPT to Slack, literally. But to help you get a better picture, just think of this bot as some search engine or an AI assistant that sits right in your Slack channel. So you could reach out to it directly with your questions and you get a response immediately. That way you don't have to switch context. For example, go to your browser. Or you could even mention this bot in ongoing conversations and have it participate. So for example, in this demo, we see two people conversing about how to set up a CI/CD pipeline with GitHub Actions. So they weren't really exactly sure how to go about it. So one of them would mention Slack GPT in the conversation, and then Slack GPT will return with a comprehensive steps on how to set up a CI/CD pipeline with GitHub Actions. This is Slack GPT, and this was exactly what Bob had in mind. But you see, before Bob could build this bot, he would have two different iterations of his architecture. Now we're going to look at these two iterations and see what we can learn from Bob's experiences. Stay with me as I walk you through Bob's thought process. Now, first iteration, Bob would build this application as a single unit. I mean, deployed, that could be developed and deployed as a single unit, runs on a single process, basically a monolithic application. This monolith will receive relevant messages from Slack via webhook. It sends these messages to ChatGPT. It gets a response and then sends this response back to Slack. Now, with regards to architecture, at this point, there wasn't really much for Bob to think about, so he moves on to what technologies to use. I mean, he's a Python engineer, so he decided to go with Python. And he's using bold Python to build this bot. Now, if you're not very familiar with bold Python, it's basically a framework that helps you build Slack bots really easily with Python. But the problem with this framework is you can only build Slack bots. So if you're building a bot like this with extensibility in mind, for example, you want to have it work on, let's say, Mattermost or Discord, then I would recommend Airbot. So Airbot does pretty much what bold Python does, but then it has literally out-of-the-box support for all the popular chat applications you could think of. Next, Bob was split. Well, he didn't really split. He would just create two Python modules within his monolith. The architecture is still monolithic, but I think at this point, Bob is just trying to modularize, for lack of a simpler word. And lastly, Bob had to decide on whether to use, asynchronous Python or synchronous Python. Now, Bob would go down the asynchronous Python route, now for performance reasons. And I say that because, for lack of a really simple word, we could describe this application as being I/O bound. And what that means is whenever a request comes into, whenever the application receives messages from Slack, it would forward these messages to the ChatGPT API, and then it waits for a response. So there's some waiting time involved. Now, writing asynchronous Python would help us, kind of manage this waiting time better to optimize for performance. I must, however, mention that there are different ways of writing asynchronous Python. For example, you could use G events, you could use Greenlets, but then Bob would go down the async.io route. Now, if you're familiar, I'm sure a lot of you are already familiar with async.io here. So if you're familiar and you've worked with it, you know that under the hood, async.io there's no monkey patching happening. So if you're going to use async.io for asynchronous Python, so whatever library you're using has to be asynchronous too. And that would explain why Bob is using AIOHTTP for his request. So now at this point, Bob has pretty much everything he needs to build his monolithic application right. But then in retrospect, he realized that there are a couple of things that could go really wrong with an architecture like this. First of all, there is the problem of tight coupling. So if you look at the diagram on your screen, you'll see that there's a direct connection between the two Python modules in our architecture. Now, this direct link creates, a level of dependency or coupling, that's the word. It creates a level of coupling that makes it really hard to isolate faults. So in practical terms, because the Slack model relies on the ChatGPT model, if for whatever reason the ChatGPT model is buggy, then the Slack module gets affected automatically. Now, if we're generalizing, like looking at the big picture, you could just say that a situation like this creates a scenario where if you have a module that other modules rely on, and that modules is buggy, then all the other modules are affected. So we end up having a system that is not so resilient or fault tolerant. We could even take this a step further. Let's interrogate these fault tolerance problems from the perspective of infrastructure. This is a monolith developed to a single server. What happens if that server goes down? The application goes down with that server too. But you see, Bob is not like you and me. Bob is obsessed with performance. So he had concerns around performance too. So Bob was worried what would happen if at some point the resource need of his monolithic application outgrows the hardware he gets. And so you could easily argue that Bob could scale vertically, maybe add more CPU cores or increase the memory space, right? Or better still, Bob could scale horizontally, create multiple copies of his application, put them on multiple servers, and then hide them behind the load balancer. I mean, I agree that this would definitely improve performance because then you're going to have multiple servers processing requests concurrently. But no, even this architecture is limited in two major ways. First of all, it is going to be really hard for you to make changes. Remember, the architecture of this application hasn't really changed. It's the deployment topology that has changed, right? So if you make a change to one of the instances, that change has to be reflected on all the instances. Now, this might not be a big deal if you just have 2 or 3 replicas, but in reality, when you work on, let's say, enterprise applications, you're going to have tens or hundreds of these replicas. Now, imagine having to redeploy to tens or hundreds of servers simply because you fixed a very trivial bug. Now, I know Bob personally, he's a very hardworking person. And even for Bob, this level of unnecessary work was a big no. And then there are concerns around how we're scaling. So yes, we're scaling horizontally, right, for performance. But the thing is, when you scale a monolith, you scale the entire application. But then in reality, even within monolith, you're going to have modules or components, and some components would have more resource needs than the others. When you scale a monolith, you don't think about these things, you just scale the entire thing. Now, taking all these factors into account, Bob thought there's got to be a better way. Now, enter the microservice architecture. This is Bob's second iteration. At this point, Bob will break down his, super large monolith, even though it's not really large in our case. He'll break it down into 2 small services that could be deployed independently. Now, responsibilities haven't really changed much. The Slack bot service will receive messages from Slack, and then the process bot message service would interact directly with the ChatGPT API. Now, the question that really matters here is, how do we get these 2 services to communicate? Well, one obvious way is to, use REST API calls. But then if you go down this route, then there's still going to be that direct connection. And then we start having the same problems we're having with our monoliths, inability to isolate fault, fault tolerance and all that, simply because that coupling is still present, right? And then Bob figured, well, he could decouple his microservices and put a message queue in between the services, basically. So in a scenario like this, the 2 services don't have to talk to each other directly. The Slack bot service would drop messages on the message queue, LavinMQ, and the process bot message service will pick up these messages and process them at its own pace. Now, the beauty of this architecture lies in the following. Christina, could you help me just move to the next slide? Yeah, so there is total decoupling, right? One of the benefits of an architecture like this is total decoupling, which makes it really easy to isolate bugs, which are a point that Christina has emphasized before. So in more practical terms now, if the process bot message service fails, because the Slack bot service does not really talk directly to the service, it will keep adding messages to the queue as though nothing happened. So whenever the process bot message service is back online, it could pick these messages and process them. Now we've isolated a failure or bug to just one service, not the entire system. Now, there's the beauty of sorry, I think I pressed now. Okay, this slide. Okay, there is the beauty of being able to scale efficiently too. Now, with microservice, you know, with monolith, if you recall, you have to scale the entire system, but then with a monolith, you just scale the services that you need to scale. So for example, if you notice that the Slackbot service needs more resources, then you could just create more copies of the Slackbot service without really having to touch the process bot message service. And then in the future, if you realize that the process bot message services needs more resources too, then you could create more copies of the process bot message service. It is for these reasons that Bob decided to, you know, I told you he had 2 iterations. First, the monolith, and he ended up working with the microservice architecture for these benefits. Now, at the very start of this, don't worry, we're not starting all over again. At the very beginning, I told you I'd tell you more about Bob, right? Now, Bob is just a figment of my imagination, a character that I just wanted to use and tell the story. But then that doesn't mean this entire story is untrue, because if you take away Bob from this story, everything else is true. And I say that because I built Slack GPT myself, and because I did, I'd be the first to admit that this story is flawed in 2 major ways. First of all, you can really argue that it is an overkill to use the microservice architecture for something as basic as this, and I totally agree. But then in my defense, right, I was working on this for a tutorial that you can find on our blog, by the way. So the objective for me wasn't really to work on a complex or, you know, realistic project. It was just to find a fun and simple project that could help me explain these concepts in the simplest way possible. The second flaw, which is probably the most important one, the challenges of working on a microservice architecture in reality are way beyond and far more profound what we've seen in this story. So let's just look at one of them because we don't really have a lot of time. Now, when you work on the microservice in reality, you're going to have tens or hundreds or even thousands, which is the case with Netflix. You're going to have a lot of services. And in a situation like that, right, you're going to have instances where a request from a client would need data from multiple services. So for example, on an e-commerce website, if you go to a product page, and hypothetically speaking, let's say that e-commerce website is running a microservice architecture under the hood, right? If you go to a product page, a request for the product detail will most likely be getting data from the product service, from the reviews and ratings service, because you need the reviews and ratings for the products too, and from the recommendation service too, right? Now, the question is, how do you get this client to communicate with your services? One way is to just make direct API calls to this service, which is what you're seeing on the screen. But the problem with that, if you adopt that technique, then you would have to, you know, for one data, like you need like the details of a product, then you have to make like up to, in our case, 4 separate API calls to get that data. Now, if you have multiple clients, you have to replicate that call across all your clients. Christina, next slide. Yeah, so you have to replicate it across all your clients, right? Now, this is not so good, but it doesn't even end here. What if in the future you decide to break, let's say, the review and rating service into 2 separate services? You'd have to make an update to all your clients too. Now, one way to solve this problem is to adopt, you know, the API gateway pattern. Next slide. Yeah, so in the API gateway, you kind of introduce an abstraction layer, right, that hides the low-level implementation details of your microservice architecture. So if a client wants to get the detail of a product, they just make one API call, and your API gateway would be responsible for getting all the, talking to all the relevant microservices. One other technique which I really didn't add to this slide is to adopt the back end for front end pattern where you create an API gateway for each client, basically. Yeah, and so, I mean, the challenges are numerous. Sometimes you have to think about data consistency too and how to deploy it. But we just tried to keep everything basic throughout this presentation, hoping that you could ask questions and we could have deeper conversations around this concept. Thank you.
Awesome.
Thank you. Thank you for a talk. We don't have any questions on Slido yet, so I'm going to start with the first question about what's the main difference between LavinMQ and something like RabbitMQ? Why create yet another broker, I guess?
Well, I guess like I said, we have a really long time of experience of hosting RabbitMQ services. So you're bound to find things that you want to change or that you feel can be more efficient. So basically, the LavinMQ project is just to try to get that into the world, basically. And so there are some performance optimizations and resource efficiency optimizations that make it a lot faster. And that's like the primary difference, that it's a lot faster. But I also want to say that it's a lot more lightweight. So it's not at all the big beast that RabbitMQ is. On good and bad terms, I guess. On good terms, that it's really simple to set up and use. And then, of course, there are things in LavinMQ that there are things in RabbitMQ that LavinMQ don't support yet. So like plugins, for example. But we're also a really small team, very agile. So if anybody has any recommendations for how we should add new features, then you're more than welcome to input or like make a pull request to the Git repository. We're always happy to take those. So yeah.
Okay, so I have a follow-up question on that one. When you mentioned that we welcome the pull request, given that the main object of the product is the performance versus, for example, RabbitMQ that is faster. How would the process of getting some major changes, if somebody wanted to contribute something, looks like? Do you basically somebody submits a pull request, or should they like ask first of like how to make some changes so not interfere with those opinionated set of opinions?
Right, so that's a really good question. It kind of depends. If you want to do the code yourself and you have a very specific idea of how you want to do it, then definitely feel free to just commit something, or not commit it, but make a pull request, and we can review it. But I think maybe that it would be actually faster to just hit us up on like GitHub Discuss, and we can implement it the way that we know how to, and yeah.
And there was one question on Slido about the tooling around. So like Rabbit has some nice admin UI, and is there any other, like for LavinMQ, is there also like a compatible set of tools or
Yeah, sure, yeah, exactly. So there is a complete UI manager that you can use, specifically if you want to use it with CloudAMQP, you even get the CloudAMQP interface, and yeah, that's also linked to the management UI. So basically, it has all of the things that RabbitMQ has in the UI.
Okay.
Yeah.
Cool. And we had some questions.
Hi there. I want to ask you a few things. First, like, what kind of technology is implemented LavinMQ? I don't know if you said it before or not. And if it's able to like scale for real-time data-intensive analytics, like can you have it like multi-process or kind of scale on the traffic?
Okay. So the first question, what technology we use? So it's built in Crystal, which is a fairly small language, pretty similar to Ruby, but it's compiled, so it's really fast. So that's like one of the performance things that we just try to squeeze in there. What like type of technology are you suggesting?
What do you mean? I was asking like, what kind of language was based on?
Yeah. So it's not based on Python, unfortunately, but we use Crystal. We really like Crystal. It's really fast, and its standard library is all in Crystal, so it's really easy for us to use and read and write. So yeah.
Yeah, and the other question was like, is it possible like to distribute like the broker on more machine, like in Kafka, for example, like you can have like multiple process, like for serving data-intensive messages.
I'm not sure if I understand the question.
Like if you have like a lot of like message.
Like a multiple node
Yeah, like
cluster?
a huge traffic, so you can like.
Right. Yeah. So no, LavinMQ is a single node broker for now. We are actually working on replication, but we have one node. But since it is so performance focused and resource efficient, it can handle a lot more traffic than a single RabbitMQ node can handle.
Okay, that's a short question.
Okay, I never use a RabbitMQ, so maybe my question seems strange. I'm a long-term user of ZeroMQ, like 8 years I use them. ZeroMQ has different patterns of communication. Now, from your last answer, I understood that this is a single server, like a star in the middle, and everybody sends and receives data through this server.
Yes.
So, what pattern of communication can you have? Just request reply, or there is also push pull, publish subscribe?
No, it's like let's see if I can. Where is my? So basically, the way that I know how to answer that question is just like to show you this this slide again. So basically, you have producers and consumers. It just goes right through the broker.
One way.
Oh, you can, yeah, one way. But you can, of course.
Christina, Christina, can I just chip in?
Of course.
Yeah, so I think I understand your question. You want to understand what patterns of communication LavinMQ supports, right? Is that what you're asking?
Yes, I mean, if you can have
yes.
different patterns, like publish subscriber with the topic. Oh, sorry. Like publish subscriber with the topic, and there is filtering, or push-pull, meaning you have you have multiple pullers. You push a message, and only one puller gets the message.
Yeah, so I think
out.
I understand you. Yeah, so from what I know so far, I think I've been working on LavinMQ for some time now too. I'm writing a tutorial. So I know that it supports the publish subscribe, right, which you just mentioned. And it supports the competing consumer pattern too, where you put a message, you add a message to the queue, and then the queue sends this message. Only one consumer could consume a message, right? One-to-one relationship too. And then there is the topics which you mentioned. So basically, the pattern of communications are tied to the types of exchanges that we have in LavinMQ. And yeah, so I know that we have the pub sub, and we have the competing consumer pattern, and we have topics too. Yeah.
Okay, thank you for the talk. We will run out of time. So thank you, Christina, and thanks, Nyior. And let's give a round of applause.
All right.